All right, good afternoon, everyone. Welcome to Cooper Union and welcome to our historic Great Hall. I'm Professor George Della Grammaticus. I'm from the Department of Mechanical Engineering, and I'm the one that many of you have been communicating with these past several months, since practically January, when you were applying, when you wanted to find out more about this program. And today's program is designed to tell you more about what we're going to be doing this summer. A number of you are undecided. I want to tell you what our expectations are of the students, and I want to tell you what the students and the parents of those students should be expecting from us. This historic Great Hall has seen many great speakers. Since 1861, we've had Abraham Lincoln, we've had the founding meetings of the NAACP. We've had the offices of Susan B. Anthony right upstairs with Elizabeth Cady Stanton. And through the years, we've had other prominent names. We've had many presidents speak here as well. And most importantly, you all will be part of that long legacy, because on the last day of our program, August 17th, starting at 9:30, everyone is invited to come join us. You will be presenting in front of a great audience at the same podium at the same lectern that Abraham Lincoln spoke at in 1861. So it's going to be a great event. It always is. I can't tell you how satisfying this summer STEM program has been for me. I've been here since 2005, my first summer in 2006. I've been teaching since then, and for the past 4 years I've been also administrating the program. So I've been managing it and directing it and performing more outreach. Since then, it was a program with 65 students. Now we're going to have well over 200. It's exploded because even though STEM activities over the summer have exploded throughout the entire nation, throughout the city, we do things a little bit differently. And that's the first thing I want to advise all of you to do as you're looking around and you're trying to scrutinize every single program out there. It's great to do something over the summer. Find an experience, find an opportunity that makes you distinctive, that makes you different from everyone else who's applying for a job or an opportunity or to a college or to some type of other activity. Okay, so do something that rounds you out, and what I always like to say is try to fail at something. Work outside your comfort zone. Do things that force you to learn and develop skills that you don't already have. Don't find the easy way out. And that's what I want to design this program to do. This is what all the faculty members in this who are involved in this program are also doing. We want you to develop these skills because that's what's going to differentiate you from the rest of the crowd. And that's what's going to make you a great engineer. It doesn't matter if you become an engineer, it's going to make you a better person. Okay? So what I want to do today is deliver the main objectives of the day. The main objectives are: did we all get here? Do we know where it is? Can we get here from home safely and easily? Are our parents at ease getting on the subway and going home? Next, we will talk about how this fits in within the entire K-12 STEM outreach initiatives that we have at Cooper. And this is just one portion of a big jigsaw puzzle where we're trying to expand the STEM pipeline in New York City and attract students to the STEM fields so that they can learn more about them. Not necessarily so that you all take a path, a career in the STEM fields. It's so that you could understand what they are more, and when you apply to colleges or when you apply to jobs, you have a better idea of what you like, what you dislike, what you're good at, what you're not good at, and what you want to do when you grow up. And if anybody asks me what I want to do when I grow up, I haven't grown up yet. I'm still figuring things out, and I'm still learning, and I'm still making mistakes. And I think that a good instructor, a good faculty member, and I think that you guys agree with me over here, is that a good instructor is always first a good student. And you're constantly a student, and that's what we're going to be teaching you during the summer as well. So we've gone down to the 4th grade, and we're trying to push down to even kindergarten right now, where we come up with these outreach activities to teach students about STEM. about engineering mainly, and basically casting the design process around the different problems that we're trying to solve. And I know everybody here under, the one-liner, what is engineering? Engineering is problem solving, right? Well, what's the first step in problem solving? Anybody? Yeah, finding a problem, really understanding what the problem is. And we're going to be doing that a lot during the summer, trying to understand what the problem really is. And in the different sections, in the 10 different sections that we have, we're going to address that first step and all the steps of the design process in very different ways to very different problems. But it's the same type of logic and the same type of critical thinking that you'll be taught. So aside from these outreach activities, we want these activities to be hands-on and experiential. What does that mean? You learn by doing. First expectation, do not expect to be sitting down in a classroom listening to a faculty member lecture for the entire day. This is not what's going to happen. This is not what happens in college. In college, every class meets around 3 hours per week. 3 hours per week. You are expected, at least if you go to Cooper Union, to work at least twice as many hours outside the classroom as you do inside the classroom. There's a lot of peer-to-peer instruction. There's a lot of learning how to teach yourself how to do things, and that's what we're doing during the summer STEM program. You're going to be given a problem. I don't know the solution. Figure it out. How are we going to figure out? Take the steps. Take the steps that we teach you. Here are the resources. What are you going to do? Are you going to take initiative? Are you going to be proactive? Or are you just going to sit there? You are going to get out of this program only what you put in. Okay? That's the expectation. From us, from our side, what you should be expecting is you will have the resources, you will have the space, you will have the time, you will have the mentorship. What we're trying to do, and this is what I've found through all these years, is that the magic combination is having about one teaching assistant or faculty member to a group of about 4 or 5 high school students. And the teaching assistants and many teaching assistants who have applied to the jobs are here right now, so that you better understand what's expected from you is that you won't be sitting in the corner just waiting for somebody to do something and just babysitting the high school students. You will be immersed in the projects themselves. You will be leading and guiding. The high school students aren't going to be your workers. You will guide them, you will learn how to teach. So just as much as for the high school students, it's an opportunity to learn the design process and engineering. For the teaching assistants, it's, hey, is teaching a great career for me? Can I look into this? Because if we need more STEM jobs, don't we need people to teach that? Okay? So we're going to be doing research, design, innovation. I say hands-on, and I want you to make sure to understand that it's not hands-only. It's hands-on, it's minds-on. That's what experiential means. It's your first exposure to engineering. For many people, it's the first exposure to engineering. The way that I compose the classes is that I read through every single application, and I looked at the students who have extraordinary experiences, who have built their own 3D printers from scratch and who have designed and built prosthetics for kids that are amputees. Great, I need you. And then I need students who, well, I don't have AP classes at my school, and I have a part-time job, and hey, look, I built this at home, and I really want to do it, and I'm very creative. Look at all of these things that I've drawn. I just need to be in a team. And so what I've tried to do is put together these classes where the teams look like they could be very interesting. And it's almost like a sociological experiment. And it's really interesting what happens. By the end of the 6 weeks, you're like, wow, how was I able to do this? So it's teamwork and leadership, and it's multidisciplinarity. In other words, you're going to have people on your team who don't look anything like you. They don't come from your neighborhood. They have skills who, wait, that's not engineering. That's more like art, isn't it? Well, you need that too. It's not form versus function. It's form and function. Okay? There's an extraordinary social mission. That's how our school was established and why it was established. And we want, in several of these sections that you'll see, we want to specifically focus on designs that benefit humankind. We want to look at the big picture. How are we going to improve the world? And for me, personally, engineering is a service profession. It's how do I serve society? How do I make the world a better place for somebody? And that could be designing engines that are more environmentally friendly, to making a sculpture that forces people to think about democracy and what that means to us. All right? So it's also, and this is a shameless promotion for Cooper Union, we want to see you guys, because a lot of you are going to apply to Cooper, and we'd like to get a firsthand feel for what you can do, what your capabilities are, because so many students, and you can't imagine how many students have 800, 790 SATs left and right, and like, there's something else. We got to see something else, okay? So what then I want to talk about is the managerial logistics. Monday through Thursday, July 10th through August 17th, 9:30 to 3:30. You take about an hour lunch. Sometimes we go overtime only if the high school students want us to. Only if you guys want us to stay longer and I could provide, I will pay TAs longer so they could stay and help you out. There's a huge crunch time at the end, and that's what happens in every engineering project. Take about a 1 hour lunch. There'll be occasional snacks. There's going to be a pizza party here and there, that kind of thing. Bring your own lunch. Bring money to eat out in the neighborhood. The neighborhood is a great place to find novel food and great new places that are opening up left and right. We'll have ID cards so that you could come into the building. We'll take pictures on the first day, then you'll be issued a card that you have to keep with you at all times. The attendance is mandatory. If you have unexcused absences, we'll talk about that later in person, okay? But just don't be absent because it's all about a team. If you're not part of the team, then you can't be here, okay? A lot of people have other commitments. Oh, I have this trip. Oh, I have this interview. I'll be gone for a week. No, then don't commit, okay? Metro cards for all. These are provided to us by the MTA, and they've done so for at least 20 years now. This program goes back close to 30 years now. We have a feeling they'll give us the Metro cards again for this coming year. If you use light rail, pass train, that kind of thing, LIRR, if there are any type of forms that we have to fill out for you so that you get a discounted rate, please send them in as soon as you can because it takes a while for things to process, okay? For many of these sections, laptops are encouraged. For instance, the computational design and entrepreneurship section, the makerspace sometimes. These are courses that sometimes it's really nice to have a laptop because you're designing all these things. Maybe you want to keep all these designs on your personal computer and then take it home after you're done with the program instead of learning a new computer. We all know how that is. Your instructor is going to give you the specifics. Once you sign on officially, the instructor will have a class list and then give you the specifics. Usually nothing very high power is necessary. Sometimes, most of the time, the computers you have are much higher power than I use, and I'm doing fine. They're encouraged, not required. In some cases, laptops are forbidden in the classroom, and textbooks are forbidden in a classroom. But that's, again, up to the instructor. It sounds crazy, right? A college professor says no textbooks, no calculators, no. Okay, so some other specifics. We're going to be working on these engineering projects, on these science projects, on research and design, but we want to develop all the skills that would make you a good engineer. We want to develop the skills, we want to expose you to the skills necessary to think critically and to find out what's out there. Now, many of you you're rising juniors and rising seniors, right? Many of you are going to be applying to colleges in the fall. We want to make sure that you see not just what Cooper Union looks like, because we're an ultra-tiny campus, 3 buildings basically, one of which is a residence hall. We want you to see much bigger schools. We want you to see Columbia, we have a Columbia Fair that we've done every year. We go up there, they have an admissions process counselor that sits down and has a seminar and a workshop with all of our students. And then you get to tour the different booths for all the different universities that are there, from small to big to whatever size, whatever part of the country, okay? Then we do an admissions seminar. Our Office of Admissions also has a type of workshop with you guys. And then we have oral presentation workshops. You have to learn how to get up in front of an audience and explain this really complicated concept that you've been working on for 6 weeks to an audience that just walked in off the floor who knows basically that much about what you just did. That's going to be a tremendous challenge for all of you. It's a tremendous challenge for me. But we have to work on those skills. So final day, August 17th, in this room. We'll have a nice lunch afterward and an award ceremony. Everybody gets a certificate of completion when you're done. And then we have technical writing sessions. Not every group is going to write a technical report, like a lab report that you write in high school. Some will be publication style. Some sections will publish websites. And that's technical communication. How do you organize the information on that website? How do you make a software manual? Last year we had one section that every single student published an app that they built in a group. Social media, maybe you're trying to promote a product that you're designing on a Kickstarter campaign. Maybe that's what you want to do. We'll help you with that. And last year in the Makerspace section, every single student left with a provisional patent application that was submitted to the U.S. Patent and Trademark Office. I mean, this is something that you usually don't get at other programs. We do things differently. Every program has a different flavor. Find the flavor that's best for you right now at this time in your life. So other than that, we'll send the parents and the guardians permission slips because we'll be taking you out. Sometimes we go on, I wouldn't call them nature walks, but if we want to discuss architecture, well, it's a great place in New York City to learn about architecture firsthand, right? We go to the museums, we go to, the Intrepid Museum is great to learn about engineering, as well as the humanistic side of things. What was happening in the country and society during the time of war. And also 4 years ago, I started a Midway Assembly where we invited 4 Tuskegee Airmen into the Great Hall, and they talked about their experiences when we had a section on flight simulation. And so they talked about their experiences. Does anybody know who the Tuskegee Airmen were? Show of hands. Tuskegee Airmen. So this is something that you should go home, and this is your first homework assignment, is to figure out who they were and what they did for this country. And then the next year, we had women in technology. We had the chief technology officer of New York City at the time, Minerva Tantoko. And then last year, I brought in a number of entrepreneurs, young entrepreneurs who I knew very well and who I wanted them to tell their story about where they started, where they went, where they're going. Entrepreneurs who, part of entrepreneurship is to fail a lot, and that you've got to pick yourself up and try something new, try something different, try to find out where the market is, okay? And this is all wrapped within the design process. Okay. So a couple of projects from previous years. We have an anxiety watch that Austin Wong, who's a senior, is going to talk to you about. We had biomechanics. We had storm surge projects. I mean, this is college level stuff. In fact, at the end of the 6 weeks, some of the projects that come out of the race car section and the Rube Goldberg section, for instance, and the gene, I remember DLD, the digital logic design, and the Professor Dell's sustainable energy, green resources, undergraduate quality work. It's incredible work what they're able to do. And last year we had 4 students who went on to get honorable mention in the Built by Girls Challenge. We've had so many students go submit their projects after they've enhanced them. to Siemens and Intel and New York Science and Engineering Fair and all that. So you may use this opportunity to submit to competitions as well, or start a company. And then forget about college, right? So other projects, we work on engines and biological material and structures and robots and concrete being crushed. And then one more slide before we, okay, so this is what we're going to do right now. I want to invite up the different instructors for the different sections. Mainly, you guys have just read that blurb that's on the website for each one of these projects. I want the living people to come up here and talk about their experiences. I want you to get to know the faces, the names, the personalities. Once we're done with this list, and I've allotted 3 minutes for everybody, all right? So it's going to be rapid fire. It's going to be up and down, right, guys? And then what we'll do is I'll answer any questions you have. That'll be the conclusion of the first portion of the evening. Then we'll have cookies and coffee before we go over to the new academic building at 41 Cooper Square. That's where all the laboratories and studios and classrooms are housed for this program. And then you'll be taken around by the teaching assistants and the faculty members so you can see the spaces. And before you do go on those tours, note that the building looks very different now inside. The classrooms look very different and the labs look very different from what they will look like in the summer. Because once classes end in a couple of weeks, we repurpose all these spaces and we turn classrooms into studios, we move tables around, we bring 3D printers downstairs, everything is on one level. I just want you to get a feel of the building, the size of the building, and what our resources and facilities look like. Okay, and then ask questions, of course, to the instructors. So first, I'm going to invite Professor Dell from the Department of Mechanical Engineering. He's been teaching this course for this section for many, many, many years, and he's got some incredible projects. So if anybody is going to violate the second law of thermodynamics, you're looking at him.
First one also.
Okay, how do you advance it? We'll talk to Austin back there. So just.
All right, Austin? Okay, when I raise my hand, I guess that means you go to another slide, okay? Okay, thank you. Okay, it's an honor to be here. I want to thank Professor Della Grammaticus, a good friend of mine who's been doing this for many years. First of all, welcome everybody. I'm glad that you're able to be here. I hope you're going to have a very enjoyable summer. My name is Professor Robert Dell, Director of the Center for Innovation and Applied Technology. Before this, I was a research fellow at MIT. I've been a guest speaker at Harvard, MIT, Columbia, quite a few other things. Academic appointments both in the United States, Mexico, Iceland, etc. Next slide, please. Okay. I talk about innovation and problem solving. What we do is we go where no one's ever been before. The good thing about it is no one's ever been there before. You know what the bad thing about it is? No one's ever been there before, so you have to make it up as you go along. A lot of the things that we're doing, people were able to prove to me mathematically were not possible, but unfortunately, reality was a little different. Next slide, please. Okay, some of the results I brought here in the last 5 years are 11 patents that are owned by the Cooper Union, and I think that sort of speaks for itself. Some in the United States, Canada, Germany, France, England, etc., and quite a few other projects. I'm sorry. Next slide, please. Okay, so how do you start with an idea? Many times your concept might start with this, and that's how many of you might start. And then next slide. It ends up more formal in its presentation. That's a skill we're going to teach everybody, SolidWorks, ways of clarifying your project so you see it. So the way I work is you always come from a point of information. In other words, you don't say, oh, I'd like to do this. No, first you find out about it. So if we're dealing with solar energy, the first thing, it might be nice if you knew what the sun was and how it worked. It's a different sort of approach. Next slide, please. Where does this result? Well, we've been able to grow cotton outside in New York City using waste heat. were able to grow banana plants outside in Iceland using waste heat. That's not possible, but the cotton doesn't know that. Next slide. Some of the projects we've done here. We've done quite a few, some with human power. Next one. And what do? We just don't do that. We do a SolidWorks model so we understand it. We do that before we build the model. Then you take your data. Next slide. And then you do all your calculations. That's one with basically a way of desalinating water using solar energy. Next slide. And then you do, of course, again, the SolidWorks before you make your actual object. Next one. And you could come out with quite a few other things, wind energy, etc. I've worked with thermoelectrics. I've also been a consultant to the United States Department of Energy. Quite a few other things. You know, you just look online for that. Next slide. Okay, one thing I want to tell you right now, since I think I have about another 30 seconds. All of you seen Harry Potter? All right, did Harry Potter have a cell phone? Okay, did Hermione have a laptop? Voldemort, did he have a face page or at least Twitter? Okay, you know why it was set back then? Because what you see then, most people now would say, I understand it. You could look at it, you could look at a watch, you could take it apart, you could understand it. Not anymore. So, what happens? Hogwarts, you came in and you could do things that most people couldn't understand, which are magic. And by the way, what engineering is, it's the discipline that changes dreams into reality. And if you think about it, you've all been admitted to Hogwarts by being here, okay? And I hope you're going to have fun here because it's going to be a very, very interesting summer. Take care. Thank you.
Okay, so next up we have Daniel Fagan, who is one of the teaching assistants for the civil engineering section. Professor Cataldo is downstairs in the laboratory, and he'll help give, he's not today, but okay, and then Max Summers is probably going to help out too. He's on slides. Okay, terrific.
Hi everybody, how you doing? My name is Dan Fagan. I am a master's student here in the civil engineering program. I just learned that I have 3 minutes, so forgive the pace. Our program has been recently redeveloped into 10 smaller experiments that gives everyone a pretty good feel of civil engineering as a whole. We have the structural, geotechnical, environmental, and water resources areas. So the first week, students come in and they're going to do some concrete mixing where they're going to try to estimate the strength of the cylinder that they will construct is capable of restraining. We're going to start here. We have 28 days of curing. So in the meantime, Max, we're going to advance. We're going to mix cylinders, and then 28 days later, we're going to take them to the Tinius-Olson hydraulic press machine, which is capable of 100 tons of force. It's equipped with a specimen brake detector to determine the compressive strength of the cylinders that have been constructed, and then eventually we will crush them, and then review the failure mode. The professor, will stop with each break and kind of go through if the cylinder was mixed improperly, or if it was a shear failure where it shouldn't have failed in that manner. Next slide. Next up, we have some wave generating experiments where we're going to analyze storm surge effects and try to create these barriers that are capable of protecting structures during these storm surges. As you can see here, we have a wave generator, and we've designed a barrier of a certain width that protects the structure from the incoming waves. Next slide. We also use some state-of-the-art software from the Army Corps of Engineers. With this, we're able to test, these high-risk areas and kind of see the effects of flooding during these high tides, and we also analyze rivers and other watersheds. Next. Here, we're also modeling in constricted channels, so we're able to place things in streams to force different conditions, and we're able to see how that affects upstream and downstream conditions, and ultimately the effects on the life of the channel. Next. And then lastly, we do some mathematical modeling of, this is my thesis actually, so we do some green roof testing. So the Cooper Union is currently working on the Jacob Javits Convention Center green roof project, and we can analyze the effect of the buffering effect of the green roof on the structure and how heat is dissipated through the different layers that are involved. So if there are any questions, you'll see me later.
Good job. Thank you, Daniel. Thank you. Okay, so now Professor Risbud will be presenting. Here you go.
Thank you, George. Good afternoon, everybody. How's everybody doing? My name is Yash Risbud. I am the director of the CV Star Research Foundation. So basically, that makes me the research director for the Cooper Union. And the best part of this day for me is all the projects you're seeing. And I'll talk about my section, but I'm proud of every one of them because almost all of them have some funded research behind them. And you should know that there are external resources that are actually funding the work that some of the faculty and students are doing. And now you're getting exposure to that work. And that's phenomenal because that's what your college experience will be whenever you get there, especially if you want to pursue research. My section is going to be digital electronics to the inventor. That's the only slide you're going to see because I just love to talk. And as my students know, there's never a PowerPoint in my class. It's me at the chalkboard or me making them do project work. And that's exactly what you're going to get for the 6 weeks that you're with me and my TAs. It's going to be split pretty much into 2 3-week segments. We kind of lay out the groundwork for digital electronics, low-level hardware. We'll be working with some 3D printers, so we'll be doing some prototyping as well, and some programming. So it's about 5 to 5.5 college credits worth of work you're going to do in 6 weeks. You will not be bored. You will be tired. And as we've experienced the last 3 years, we've had to keep the lab open during the last 3 weeks afterwards because students want to stay, and they want to do work, and they want to ask questions. And it's really a feedback process to make sure that we're doing our best job for all of you, and no one gets left behind. Everyone comes in with a different level of expertise. And as George was saying before, no one's a number, everyone's a name. And we make sure that each of your sons and daughters will know that throughout the entire 6-week process. We have extraordinary TAs. All of them are undergrads or graduate students, and almost all the ones that I hire have been through my class. I teach this class to all the freshman electrical engineers, and have been doing so for, someone reminded me, for 20 years. So it's been a while. I had black hair. I had a full head of hair when I started doing that way back when. And I'm also a graduate of Cooper Union. So I love this place. I spend all day and all night trying to do my best for this place. And that means working hard for our students and working hard for all of your sons and daughters in all the work they're going to do. Their final projects, when you come see them at the end of 6 weeks, will be extraordinary. They will have created all kinds of things, from replicating video games to creating robots that they've never, ever had experience with before. The primary principle that we use in the classroom is when you're done with the Cooper education, you have learned how to learn, and that will stay with you for the rest of your life. It is by all means the fundamental part of what differentiates a Cooper Union graduate, a Cooper Union student, a Cooper Union faculty member from everybody else. We're proud of that concept. We work hard at it. And over the summer, the best part for me is I don't have to grade anybody. I get to be there in the lab. I get to be there in the classroom as with my TAs, and we get to really interact. And you may not think it's a fun topic, but it absolutely will be when you're done with it. We'll be around later to answer any questions that you have. And good luck with your decision making. We hope to see you this summer.
Thank you, Yash. Thank you. Okay, next up is Professor Medvedik, who's the director of the Kanbar Center for Biomedical Engineering here at Cooper Union. I did want to highlight something that Yash just said about grading. And what I think is most important is it's not just the grades, it's the experience that you have. And so take advantage of this experience and work as hard as you can and try to make as many educated mistakes as you can, because it's all about what comes out of this. Nobody's going to look at the grade. Who cares about the grade? It's what did you build? What did you design? What did you learn? Okay? And this is the first time that we're going to be offering the cricket biome. This is one of Professor Medvedik's many research projects in the Biomedical Engineering Center. I'm really excited. I hope you guys will be providing lunch on the last day, right? The crickets. Right.
Hi, everybody. So as George said, I'm Professor Oliver Medvedik. I direct the Kanbar Research Lab up in the new building on 41 Cooper Square. And you're probably wondering what the Cricket Microbiome Project is, or the Golden Cricket Project, building nutrient-enhanced edible insects. And that's just a screenshot from a crowdfunding campaign we're building for a website some friends of mine run called experiment.com. Well, you'd probably be surprised to know, maybe some of you eat insects. How many people here have eaten a cricket? Yeah, quite a few hands. So there's about 2 billion people on Earth who regularly eat insects and get their protein from insects. So 2 billion people can't be wrong. And it's actually creeping into the West. Next slide. So this is something I found online from ThinkGeek. Wasabi-flavored house crickets, bacon and cheese-flavored grasshoppers. And why insects, right? Because, well, they're a pretty nutrient-packed resource. They have a lot of protein, and they can be cultivated in very small environments. And they're not only good for the environment here on Earth, but they're actually a compact source of nutrients for out of Earth. So if you're going to go to have a Mars colony or on a space station, you can't bring cows up there, but you're going to have some sort of protein source. So what we're trying to do here is really kind of radically combine that with genetic engineering or synthetic biology, which is constructing new living systems for the benefit of humanity. Next slide. So this has been inspired by a project. I don't know how many of you have heard of the Golden Rice Project. This took place about 15 years ago. This is a variety of rice that's been genetically modified to produce beta-carotene, which is the precursor of vitamin A. So about 100 million people every year suffer from blindness as a result of vitamin A deficiencies in their diet. So that golden rice there is actually enriched with beta-carotene. That's what gives carrots their orange color, right? So the way this rice was created, next slide, is by basically taking parts from other living systems, parts from daffodils, parts from bacteria, and these parts are genetic parts, and they've been modified in such a way they can be recognized by the host that you're going to put those parts in. And since everything on Earth has evolved together over eons, we all basically run the same operating system. That's why you can take a human gene, put it into a bacteria, and make human insulin. Otherwise, it wouldn't be possible. So in this case, what we're going to be doing is constructing the vitamin A biosynthesis pathway, not in the grasshoppers or the crickets. That's a little difficult. So what we decided to do instead, in this case, is to take all the parts and put them instead into a probiotic, which is easier to work with. Next slide. So what are we going to use? Well, we're going to look for bacteria. And one type of bacteria is lactobacillus. We eat this all the time. This genus is in yogurt. And if we genetically modify it, we can quickly see that we've modified it because it's going to turn an orange color. It's usually about a whitish color. The other part of the project is looking for a microbe that can actually live in cricket guts. So once you have this critter created, it can then be fed to the crickets. It'll populate the cricket gut. And instead of feeding the crickets vitamin A all the time, they will basically have a little vitamin A bioreactor in their guts. And then we'll be able to measure how much vitamin A is produced. So we'll basically have super nutrient-enriched crickets that have been genetically modified. What can possibly go wrong? Yeah. So there's a lot of parts to this. You're going to be working in most likely groups of 4. Every group is going to be working on a different subsection, a different subassembly of the genetic pathway, and you're going to have TAs that are going to guide you who are all experienced, that worked at iGEM, which is the International Genetically Engineered Machines Competition. And this year, this project is going to go on to what's known as the Biodesign Challenge, which is held every year here in New York. And we hope by the end of the summer that we're going to have some genetically modified probiotics creating vitamin A. Thank you.
Thanks, Oliver. Okay, I just work on cars. How awesome is that? Here, Earl. I want to introduce Earl Coe. Earl Coe is part of our STEM outreach program. He is a faculty member in our STEM Saturdays program, one of the only Saturday STEM programs in New York City. And he also was a section leader, a lead instructor last summer in our summer STEM program. And that's the section that everyone submitted, published an app, and they built it from scratch. Some people didn't even know anything about code. So that was great. It was great. So.
Thank you, George. So last year, George reached out to me back in June, I think, for like a July course. And it's like, actually, no, I didn't. I reached out to you No, I don't remember. I don't remember. You know, it was a reference from a mutual friend of ours. It's been a blur. But I was like, well, I know computer science and I know a little bit of entrepreneurship. Let's teach this and try to jam pack approximately, let's say about 3 semesters worth of undergraduate computer science into 6 weeks. How is that possible? And along the way, make a business out of it. So computer science entrepreneurship focuses on both the lean startup methodology and foundational computer science skills. We, over last summer, within 6 weeks, we were able, myself, a co-instructor, and 4 TAs were able to guide 20 high school students, juniors and seniors mostly, from basically no computer science knowledge to a working app, a fully working app, and one of them, maybe 2 of them, were able to publish to the App Store as well. Now, that not only were they working apps, there were also apps that had a demonstrated need in the community. And if anyone's familiar with Lean Startup, they'd realize that the Lean Startup methodology is mostly the scientific method applied to making a business. It's a lot of trial and failure, it's a lot of interviewing, it's a lot of customer development to be able to develop a software. One group did make a little bit of a hardware aspect to it as well, using Arduinos. So creating a product essentially that people have a need for and that people can actually use. So, you know, one of the one app that did make it onto the App Store within the 6 weeks was Pick Event, and that you can download it right now. It works. It worked for 6 weeks. It worked. And within the course of 6 weeks, it was developed, and that was, I think, was fantastic for that team. Other teams, they got close to publishing. They didn't get to publish. They might have published after the fact as well. But in any case, I could talk about that one project, and that one project was take a picture of a flyer, and immediately it's automatically added to your calendar. And that's like a super simple thing, and they built that all within the course of 6 weeks. So we took those students from 0 computer science knowledge to a good, maybe at least a first-year undergrad in computer science, and of course throw in a little business in there as well. I'll be around for any questions.
Thanks, Earl. Yeah, and just to highlight, again, what Earl said is that the first step in the design process is to find out what the problem is, and the lean launchpad methodology that Earl's talking about is just, for me, it's just a restatement of finding out what the problem really is. And the problem is, what does the customer want, or what can you tell the customer that, hey, customer, this is what you need. Okay, so next is Austin Wong. He is a senior mechanical engineering student at Cooper, and he was a co-instructor in Makerspace 2 years ago, right? Great. So here we go, Austin. I'll be right up here.
Sure thing. Hi, my name is Austin Wong. I am a mechanical engineering major, and I'm about to graduate in a month. So, in the first slide that I have, I'd like you guys to just take a look and observe what the environment is like once it comes up. Technical difficulties? Nope, that's not it. All right, that's it. Yeah, so I want you to take a look and just see what kind of environment these students are working in. You'll see students at the chalkboard. Some of them might be confused. Some of them might be having fun. Some of them might be facing a challenge they've never faced before. Others will be confident because they have a team of TAs and other students to help them. Students are divided into groups of 3 or 4, and they start with a project that they've probably never had any experience with before. But they're doing a project that they feel is meaningful. As Professor Dalgrammaticus has mentioned, this is the session where students will come up with an idea, an invention, and bring it all the way to the fruition to the point of being able to file a provisional patent application for it. So, next slide. A lot of this program has to do with the design process, going from a design to a prototype and then documenting it. Typically nowadays in engineering or at Cooper, students will design using, well, sketches or 3D CAD software. CAD software is computer-aided design, and typically SolidWorks or AutoCAD will be used. If you've never had any experience with it, that's fine. We'll teach you. And we think that this is a really valuable experience because you get to have something virtual in front of you, and instead of having to spend all this time trying to figure out if it's going to work and wondering what it looks like, you can actually build it virtually. And the best part is you can actually make it. You don't have to use clay or necessarily go to the machine shop all the time and take hours to make it, but now we have rapid prototyping. We have 3D printers and laser cutters, so that way, in order to get your idea to a physical prototype, it might only take a matter of hours instead of days or weeks like it was in the past. So 3D printing and laser cutting, these are some of just the cutting edge technology of rapid prototyping that you can be immersed in if you're participating in this program. Additionally, last year's projects included smart gardens, included a bracelet or watch or wearable that allows you to prevent anxiety. There's also been technologies that improve upon coloring or 3D printing, and also an invention that allows students to generate energy from waves. So if you'd like to hear more about some of these projects or what we worked on 2 years ago, definitely feel free to just come up to me and ask. I think that this is a very valuable program, not just for learning how to gain new skills in engineering, but also in understanding yourself and what makes you a creative person. I think everyone has a bit of creativity in themselves, and if you can bring it out, you can realize some dreams that you've never realized before. Thank you.
So what you'll see is a couple of common themes, especially between the computer science and entrepreneurship and the makerspace and the digital electronics groups specifically. A couple of years ago, we only started with makerspace, and we realized that there was this certain need for business and entrepreneurship. So we split that section up. And then the digital logic design, the digital electronics section was purely electronics-based and purely hardware-based. And then we've evolved that to now include prototyping and to include some of the business aspects that we were teaching in the other courses. So there's going to be a lot of overlap in the concepts between these three specific sections. Now we're going to talk about race car engineering. It's one of the sections that I'll be leading, co-directing, and Randy Hilston is going to be presenting for 3 minutes.
Hi, everybody. I'm Randy Hilston. I'm a freshman mechanical engineering student here at Cooper, and I'm going to be talking about race car design. Next slide, please. So every year at Cooper Motorsports is one of the largest organizations here at Cooper. It's part of an organization called Formula SAE, which is run by Society of Automotive Engineers. Every year, we design and build a car from the ground up, all done by students. It's very exciting stuff, and we go to Michigan, and we compete internationally with teams from all over the world. And so where you guys come in is after we compete in Michigan in May, we have a lot of design goals for the next year. And what you're going to do is you're going to prototype the next generation of our car. Next slide, please. So these are some examples of previous projects that have been done at Cooper during the summer STEM program. So if you see in the top corner or top left corner, we have pedals. Last year, a group of students designed adjustable pedals so that taller and shorter drivers would have better ergonomics in the car and more easily use the pedals. We've also done things like the nose cone there. So all of our body work is done in carbon fiber, and students last year, or 2 years ago, prototyped a carbon fiber nose cone using the wind tunnel that we have in the motorsports lab, using yarn tufts and visualizing the flow going over the surface. And so you will be able to do all this stuff yourself. Being able to do composites work, I think that's pretty exciting. And so everything that you're going to do is going to be done in scale and is done as a prototype for the formula team to take the next year and expand upon it and build a better car. Also, so a potential thing, we've worked with carbon fiber steering wheel in the past. That was a big project last year. And so a potential project this summer would be shift lights. So that tells you when your car is at the optimal RPM to shift because you're past your power band, and so then you'll get better performance. Also this is something that's very close to my heart. So last summer, a thing called an under tray was prototyped in the wind tunnel. An under tray is an aerodynamic device that goes underneath the car. And so through EID 101 here, taught by Professor Della Grammaticus, we were able to take that data and build a full-scale one with myself and a group of 3 other freshmen. And so a full-scale under tray, done by freshmen at the Cooper Union. It's pretty exciting stuff. So this is the kind of things that you're going to be doing over the summer. Next slide. So some of the skills that you can plan to learn, you're going to learn about everything. It's not just a mechanical engineering section. So you'll learn about soldering. You'll learn about electronics. You'll learn CAD software, as you will in many of the other sections. We'll primarily be using SolidWorks. And so you don't have to know any of this stuff before coming in. We don't expect you to. We will teach you everything, and then by the end, you're going to be pretty darn good at it. And so, as I talked about before with the nose cone, you're going to learn composites. I mean, where else are you going to be able to learn how to work with carbon fiber? I mean, I think that's really amazing. It's something that I love to do. Material of the future. But a big, important part is learning how to communicate with others. You know, if you can be the best designer in the world, but if you don't know how to communicate your ideas to your peers, how are you ever going to succeed? So that's something that you'll definitely learn in this section. So thank you all for coming, and hope to see you over the summer.
Thank you. Good job. Great job. Great job. To one more sentence on the race car section. So the high school students over the summer are basically the research and development arm of the formula team. And what we try to do is we have the students try out crazy ideas that maybe this will work, maybe it won't work. Don't expect everything to work. That's the whole point behind research, as Professor Dell said. You're going somewhere where nobody has ever gone before to innovate. So we're going to be doing a lot of projects. We have many more projects than that Randy showed you that I'd really love to do, and maybe some are a lot crazier than others, and I don't care if you call me crazy. That's just who I am. And speaking of crazy, the last section I'm going to talk about is one that I started in 2006 exclusively with the Manhattan Comprehensive Night and Day High School. And in 2006, the administrators from that school came to me and said, hey, we have a group of 16 students. They're all very recent immigrants, and they don't know English, but they've done great in physics and math. Can you do something engineering-wise with them? And then I thought, and many of you have seen this concept over and over again in all of these slides, is that spatial, two-dimensional, three-dimensional spatial visualization is the first step into developing your problem-solving skills. And so what I wanted to do with this section is, this is the one that I said, no textbooks, no equations, I don't want to see anything but drawing. I want you to think creatively, I want you to use only resources that we get from recycling bins, from the trash, from home that's being thrown away, and then a certain number of things that I provide to you. And can we come up with a kinetic sculpture that starts and finishes in the Rube Goldberg manner and does something very whimsical, but it exposes something very important about society. And I've had projects in the past where we look at sustainability and energy, and we look at architectural prototypes throughout the world. And So it all starts with this cartoon, and I want every student to pick up a pencil and a piece of paper, and I know a lot of that doesn't happen anymore because of all the computers, and I want you to draw. I want you to draw an idea. And as we progress through the 6 weeks, we start with mini projects and mini competitions. Who can build the strongest bridge that can carry this, or who can take this motor and pull the heaviest weight up a table, that sort of thing. We go from one discipline to the next in mechanical and electrical engineering. Many touch on chemical and civil engineering as well. We take fans out of old computers. They're thrown in the recycling bin, and we learn fluid dynamics. We take pumps out of devices, and we learn about pump curves, and we learn about energy efficiency. And then they're supposed to creatively put together all of these different parts so that they make this machine. And in years past, it was a typical Rube Goldberg machine that starts and finishes, and that's it. But starting a couple of years ago, what we did was we built machines, and all of these parts now is where we went to CAD, and we brought the computers into the classroom, and we have laptops that now program the microcontrollers. We have machines that start and stop and then start again. So they're continuously operating machines. And they're kinetic sculptures that my hope is that we build one gigantic kinetic sculpture that brings together all the group's projects in one that can be powered by the sunlight that comes in through the windows of the corner of the 41 Cooper Square building. And it's also activated by people walking by, and when you come closer to it, something happens, and you interact with it through the window. So that's my current idea. And in the next slide, these are 9 projects that we did last year, and they all worked. It was incredible. I do have one project. You see the hyperlink with the theme Olympics, Austin? If that works, it would be really great for you guys to see this. And every student was responsible for one step in this machine, and even though there are only 4 steps, it took 6 weeks to build all of this. Okay, so what we can do is scroll through halfway. They videotaped this the same day that the Rio Olympics opening ceremony was, and this was basically their opening ceremony in tribute to the Rio Olympics, where we start with a motor that was salvaged from an old 3D printer, a really old 3D printer, bicycle chains. We go to bicycle shops all the time and say, please, 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 do you have any garbage? And then magnets on this chain. There's a steel ball bearing that's carried up through those magnets, and that represents the diver who dives into a pool. And then we go through the golf course, because it was the first time that golf was in the Olympics this year. And then the ball goes into a catapult, which represents the basketball player. The basketball then gets shot into the basketball hoop, goes down a ramp, and then we play beach volleyball, which is such a great sport in Rio, and then we go back into a funnel to start over again. And you can't imagine how long this took. You know, it looks simple, right? But when you draw a seesaw on a piece of paper, building it is a lot harder than drawing it. And then having it link with all the other parts is nearly impossible. So here we go. And sorry about the music not being there, but this is the Olympic theme. So here you see the ball, right? It's right there. It's going down. Now it's going through the golf course. And they timed it so that it falls into this bucket, goes in there, and they have a cam right there with a motor, and it bounces back and forth a couple of times. It took weeks just to get that bounce correct. Okay, so that's the kind of thing that we're going to do. Thanks. And we have these projects going back to 4 or 5 years online. All you have to do is in YouTube, you just search for Cooper Union Rube Goldberg, and they all come up. So a lot of great projects. I'd like to answer questions right now, and then what we'll do is we'll split up into the different groups according to your rows, and you'll follow the person that leads your group. Computer science and entrepreneurship. You guys will come back because it's basically a classroom with computers, and then we could tour after you're done with cookies, and then everybody else sort of kind of has a lab to go to. But what we'll do is go with questions first. And then we have an extra microphone so everybody can hear the questions. Here we go. I'll just run up. I'll get some more cookies. So here.
It's a boring question. Can we get access to these slides?
As a matter of fact, I'm going to put these slides up. It's one presentation file, and we've also videotaped it with audio, and what we're going to do is convert that and post that online. And what I'll do is I'll email that link out to everybody and also post it on our projects page so everybody can review it when you get home, because I know this was a lot of information all at once. Okay? Good question, thanks. Speaking of which, make sure that your spam filters don't filter my email out. It's georged@cooper.edu. We've gotten a lot of that this year, unfortunately. And whenever I do the automatic form letters to everybody, a lot of people don't get them. So what I'll be doing this year as well is I'll be using Twitter and Facebook to update. So just link to that. In addition, I've started a Transportation Buddies group on our Facebook page because I found that a lot of people like to get together at a train station and go home together and come to school together, or meet at a certain station and come in, okay? So we could use that. Anything else? I can't really see, but don't be scared to ask.
Can students from different sections work together?
Oh, unfortunately, that's, I'm not one to say no to interdisciplinary work. So I'd like to hear a proposal. I'd like to hear a proposal before I say yes or no. If it's a great idea and it gets the instructors' hearts going, yeah.
For example, so the ideas that the students worked with, the work that the students worked on last summer were their own ideas. And if any of those ideas took aspects from computer science and makerspace, there's some opportunity for collaboration there. One project that someone worked on was an app that had a hardware component that measured the air pollutants in the air. So there was a little bit of a hardware component there, and interfacing it with a mobile device to collect data about the air quality. So that's a possibility.
Definite possibility. We just have to see if we could arrange the logistics. I'm all about bringing people together. Good question. Good question. Yeah.
After seeing the presentation, if we want to move our section, is that allowed?
Ay, ay, ay. Oh, no. It's really difficult right now to change. I will have to wait until May 1st, and then maybe a couple of days after May 1st, because May 1st is the deadline for the deposits and for the yeses and the nos, and the official yeses and the nos. And then what I'm going to do is find out how many spaces we have left. As it is with college, I've over-admitted because I know not everybody is going to accept our offer. There are many other programs in town and in the country and in the world that people go to. So I'd like to find out what my numbers are. I'd like to keep the total number in the class to a manageable limit. And then if you do want to change, then you'd have to just email me and I'll put you on a list before I go to the wait list. Okay, so you guys who are here have priority in switching before I go to the wait list, but it all depends on whether or not there are too many bodies in the class. Okay? Not just a safety issue, but also from a pedagogical perspective, too many students, you don't get that personalized attention. Okay? Trust me, no matter what section you're in, it's going to be awesome. I think that, yeah, that's what I'm driving for, is just an awesome experience. Anybody else? That's it? Ah, great.
All right, so my question is, do students get the opportunity to interact with each other on a social level, exchange ideas, kind of discuss what they're working on? Is that something that's offered?
That's a great question, and it's one of the challenges we've had. We have the lunch hour that they could interact. They could interact during that hour. Having over 200 plus students, it's a difficult thing. Across the different courses. So how do you find out what's going on in the other courses, and how do you communicate between courses? I think this is a part B of this question, this great question that was over here. That's a hard one. It's a hard one to manage. You know, there's a lot to pack in, and I completely understand the issue there. I think that one great way of doing it is like what we do in our freshman engineering design class is in the middle of the program, let's have a review of what you've done in here and do a quick, not a 20-minute presentation, but a 10-minute presentation. This is what we've learned, this is what we've done, this is how we've done it. So that students get a perspective of the sheer variety of engineering problems out there and how the same engineering design process can be applied to anything out there. Yeah, that's a great new direction for us, I think. Yeah. The eyes are the first thing to go, you know. And then the hair.
Just kind of a housekeeping question. You had said that in one of your emails that we'd have the opportunity tonight to present our deposits. At which point would we be doing that?
Okay, so after the tours, I will be stationed at a table in the front lobby of 41 Cooper across the street. And then you could drop them off there. Okay?
Will we be able to keep the modeling software that we work with during the program on our computers?
Ooh. The programming software for sure, because a lot of the programming software is going to be web-based, right? Yeah. And in many of the projects, we provide you with a lot of the electronic kits. And by kits, I mean just a box that's full of all these different electronic components and microcontrollers, and you use those as your hardware. Not that it's basically a Lego electronics kit, and now you just read the book and do exactly what's in the book. That's not what we do. And some students take that stuff home after they've done with it. But things like SolidWorks and AutoCAD, I don't know if computers are powerful enough to do the kind of thing that we need in the first place. However, when you do get to college, the student versions of those are $150. So basically, a cheap textbook. Isn't that crazy? A cheap textbook is $150. So yeah. Oh, right. Yeah. So what we should do is give everybody a list. Right. Super expensive. Yeah. There's a lot of great stuff for free out there.
I have the following question. Do you practice when, say, once a week, say on Friday afternoons, Thursday afternoon, students share with other groups, just 10 minutes talk, representative from each group, what is done during the week. It will motivate the students to compete in positive sense. Also, the students will practice to deliver essence during 10 minutes, for example, and will, I believe, enhance and improve the final day. What do you think about that?
And absolutely, this is a great question, both from the technical writing and the technical oral presentation perspective. We don't just leave all of that until the day before the final presentation day. Writing and technical presentation skills are critical to understanding the problem. So every group within the section is going to get up almost every day. I mean, I start with presentations on the first day. And within the group, you learn a lot from what's going on, and there's the competition to spur everyone on. Between the groups, what we're going to try to do is somehow have other sessions where they, that we haven't had before, where they communicate a lot sooner than the final day. But you'd be surprised, there's a lot of communication between the groups just on a social level during lunch. Yeah.
Just wondering, how will the days be divided up? Will it be like first week is all lessons, then the rest, or will it be like a lesson a day or something?
That's a great question. That's very different for every group, and it's very different for each group. It's very different depending on the students who are in the class. So we try to personalize, and I'm speaking about my section, is I personalize to what the students' needs are and where they want to go with the projects. And then if I stop all work, come to the blackboard, let's have a 15-minute lesson on this, and then go back to your work and do this, that's generally what I do. The first maybe 2 weeks, you have more of the blackboard style. I think you should expect close to a 45-minute blackboard in the morning, and then maybe another 45-minute to half hour in the afternoon during the first 2 weeks. But if you look at the structure of a lot of these classes, it's work session all day long, work session all day long, practice presentation, technical report, seminar. Okay?
Let's say if you want to learn machine learning, will we be able to learn beyond the course level?
That's also a great question. If you have particular interests, and I think this is part of the computer science and entrepreneurship one, if you have specific interests, specific projects in mind, you would explore those in your project. And that's exactly what an authentic engineering process is. An authentic engineering project is, hey, you've got an idea. No, you didn't learn all of that stuff when you were in college, but you learned how to learn that stuff and learned how to teach yourself that stuff. So you would have to go and learn how to learn, but we'd show you how to do that. Yeah. Good question. That's basically what life is, right? Okay, I don't see question. Oh, wow. A lot of questions. That's good. That's good. Who?
After the program is over, would we be receiving any high school or college credit?
That's a great question. Currently, no. But we know that from a number of these sections, the end product is of quality of college level, several credits at least. And so in order to explore that, I would have to get this passed through the curriculum committee, through a faculty committee, before we do that. Yeah. But that's something that's been on my to-do list. And there would have to be grades. You would have to register. There would have to be, yeah. Grades, yikes. Okay, so what I'm going to do now is, we're running a little bit late, but I think these were really important questions. It's 10 to 7. Wow. Okay. Let's get coffee and cookies, but you know what? It's going to be like a wedding. We'll start with, what's the last group in the back here? Okay. Sustainable energy and green resources. That is Professor Dell. And why don't you go out there? And then the next section would be modeling New York City sustainable infrastructure. This is the civil engineering section. That's with Max and Dan over there. And then let's do digital electronics with Professor Rizbud. Yeah. Yeah, we're going outside, getting cookies and coffee if you want them, and then make sure you chase down the person who leads your group and go with that person. Any questions as we wait for that? Maybe we should have race car. Okay, okay. Oh, in our undergraduate and in our undergraduate program, we have a total of 1,000 students. That is divided between the School of Art, the School of Architecture, and the School of Engineering, 3 different programs. The School of Engineering is about 50% of the students. Art, about 35%, and architecture is ultra tiny. It's about 15% of those. And our engineering school is divided into 4 degree-granting departments: mechanical, electrical, civil, and chemical. And we also have a Bachelor of Science in Engineering program, a degree that is our version of a general engineering degree, where in that general engineering degree, you are required to take the same core curriculum as every engineer. So the fundamental math, the fundamental physics, the fundamental chemistry for the first year and a half or so. And then what you do is you craft the rest of your schedule, so that if you want to become a doctor, you take all the biomedical engineering courses you can, all the advanced bio courses, all the advanced chemistry courses, and then you get ready for med school. If you want to become a lawyer, you take entrepreneurship, you take patent law, you take those things. If you go into finance, and many companies, many banks come here specifically to yank our engineers out of the engineering field because they know how to think. You take engineering economy, engineering management, finance, microeconomics, macroeconomics, etc. Okay? Yeah. Computer science is going to go in that corner over there for now. Yeah. Okay. How does that hallway look? Is it full? It's full, huh? Okay. Wow, we're bursting at the seams here, which is good and bad. Any other questions? No? Pretty intense evening, huh? A lot to digest. Yeah.
Do you have any returning students from previous summer camp?
We do have not even a handful of students who come back, but they do come back. About 10% of our admitted freshmen in the engineering school have come through this program. But usually a follow-up, if you really, really love the program and there's a different subject you want to do, that you have a project or you want to continue a project, it would be great. But I would advise looking at something else. I would advise going to a different program so that you could see how other schools do it, and maybe even not in engineering. We have an art program over the summer for high school students, an architecture program. We have a summer writing program. I would try to get other experiences. You know? Not that I wouldn't love to have them again, and we've had them again, but you got to really broaden your horizon because for many of us, it's a little too early to commit to a path. You know? Good question. Yeah.
Could you talk a little bit about the Saturday art program?
I know about the Saturday STEM program. I don't know about the Saturday art program. The Saturday, other than there are two Saturday programs in the art school. One is called the SATPRO, Saturday program, and the other is called the Outreach program. And the Outreach program is taught by students at Cooper, and SATPRO is taught by faculty here, and adjuncts and instructors. The Outreach program is free, and it's for New York City public school students only, and it allows you to prepare a portfolio for college admissions. And the Saturday program, they do a lot of cool stuff too. Yeah. Our Saturday STEM program, which we had our first fully funded semester that just finished on April 1st, and Earl was the lead there. We have 10 straight Saturdays, and it's free for the students. You get your Metro cards, you get fed, you get a microcontroller kit, and you get a laptop if you finish all of your assignments to take home at the end of the program. And it's basically take what Earl does over the summer in the computer science and entrepreneurship with a little bit of what Professor Risbud does in his digital electronics class, put it together, squish it into 10 weeks, 10 days, really. 10 days. So it's like one hackathon after another. And in the fall semester, we focus on 2D and 3D visualization skills. So we teach you SolidWorks, and we have almost like a Shark Tank presentation at the end where you go up in your small company and you try to pitch this to a hypothetical set of venture capitalists and judges. And you have a product that you design and build from scratch. And so that's more on the mechanical and electromechanical side. And in the spring semester, it's more on the microcontroller computer science and entrepreneurship side. And those applications should be up in about 2 weeks, if you're interested in those.